All right, in this video, we will be starting chapter 2. In chapter 2, we'll be talking about derivatives. We are going to start with section 2.1. 2.1 is about an intuitive introduction to derivatives. Okay, basically, we are going to understand the idea of derivatives geometrically. Okay. All right, I want to start with this definition. Slope of f of x at the point x is equal to a. What do you mean by the slope of a function at x is equal to a? Okay, the given function is f of x. Let's see what we mean by the slope of f of x at x is equal to a. Okay, here is the definition. The slope of f of x at x is equal to a is the slope of the tangent to f of x at the point x is equal to a. By the way, the slope of f of x at x is equal to a is denoted by f prime of a. We pronounce this as f prime. This is the prime symbol, f prime of a. F prime of a means the slope of f of x at x is equal to a. Okay. And I want to introduce another name for the slope of f of x at the point x is equal to a. Slope is same as the derivative. Sometimes we say that the derivative of f of x at the point x is equal to a. It is the same thing as the slope of f of x at the point x is equal to a. In other words, the names slope and the derivative, they are the same. Okay. And they both are denoted by f prime of a. This is the slope of f of x at x is equal to a, or the derivative of f of x at x is equal to a. All right, let's try to understand this geometrically. Suppose you are given the graph of a straight line. Say this is y is equal to f of x. This is a straight line. If this is a straight line, we all know that from your pre-calculus, this has a constant slope, right? The constant of this straight line, slope of this straight line is a constant. Okay, usually straight line takes the form y is equal to mx plus c. This m is what we call the slope of this straight line. Okay, the slope is constant. But what if we have a function other than a straight line? What if we have a function of this form? Let's say this is your function y is equal to f of x. Now, if I ask you to define the slope of this function at this point x is equal to a, how do you define the slope of this function at x is equal to a? Okay, that's the idea. Okay, we need to have a way to define the slope of this function at this point. If it is a straight line, of course, the slope is a constant. Okay, it's a constant value, but in this case, how do you define the slope of this function at x is equal to a? What you do is you draw a tangent at this point to the graph of f of x. So if I draw a tangent to the graph of f of x at that point, you get a straight line like this, right? If you draw a tangent at x is equal to a, this is the straight line that you get. This is the tangent at x, tangent to f of x at x is equal to a. Okay. So the slope of the function at x is equal to a is defined to be the slope of this tangent line. Okay, that's how we define the slope of a function at x is equal to a. It is the slope of the tangent to the function at x is equal to a. Okay, or in other words, the slope of this tangent line. Okay, now you should be able to tell me, if I give you another point, what would be the slope of, for example, if I give you this point b, what would be the slope of your function at x is equal to b? So you have to draw a tangent at that point, and you take the slope of that tangent to f of x to be the slope of f of x at x is equal to b. Okay. All right, let's move on. Next, we need to be able to sketch the slope functions given the graph of the function f of x. Okay, so let's see how to do that. Before we do that, I want to recall you something. If a line is slanted upward, let's say this is your y-axis, this is your x-axis, And if a line slants upward from left to right like this, then this line has a positive slope. Okay, this line has a positive slope. Your M is positive. But if the line slants downward from left to right, then this line has a negative slope. Okay, slope is negative. That is something that you learn from your pre-calculus class. Okay. All right, let's look at this one. Sketch the slope functions of each of the following. Okay, so this is the given graph to you. Clearly, this is a straight line. Let's say that the straight line is y is equal to 2x plus 1. How do you draw the slope function for this particular function, for this straight line? We know that if this is a straight line, the slope is a constant, right? How do you find the slope if the equation of the straight line is given? View this as y is equal to mx plus c. Then m is your slope, right? M is your slope. M in this case is 2. Notice that your m is 2. So the slope is 2, which is a constant. So the slope function would look like this, with this value being 2. Okay, slope is constant. That means we should get a horizontal line like this. The value of the slope is a constant. Okay, so this is the slope function. You have the slope on the y-axis. All right, that's the slope function for this straight line. Now let's try to draw the slope function for this particular function, graph of the function given to you. Okay, so let's say this graph is the graph of the function y is equal to g of x. How do you draw the slope function for this particular function? Well, first of all, notice that at x is equal to 2, what is your slope? By the previous definition, the slope at x is equal to 2 is the slope of the tangent to your g of x at x is equal to 2, right? If you draw a tangent to your function g of x at x is equal to 2, that function is horizontal, right? As you can see here. So if that tangent is horizontal, what is the slope of that horizontal line? Slope of a horizontal line is 0. Okay, that is again something that you learn from pre-calculus class. Slope of a horizontal line is 0. So that means the slope at x is equal to 2 is the slope of g of x at x is equal to 2 is 0. What about the slope of g of x to the left of 2? In this region, what do you think? What would be the slope? Slope is clearly positive. No matter what point you pick, if you draw a tangent to your g of x at that point, that line slants upward from left to right, right? So that means the slope is positive. No matter what point you pick, the slope is always positive. For example, if you pick a point somewhere here, and now if you draw a tangent here, again, your slope is positive. Let's say you pick a point somewhere here, and then if you draw a tangent, again, your slope is positive. Okay. Likewise, as you can see, as x approaches to 2, the slope is approaching to 0, because at this point, you notice that your tangent line is a horizontal line, so the slope is 0. If you take a point which is very close to 2, that tangent line is almost horizontal. What does that mean? That means the slope of that tangent line is very close to 0. So how do you draw the graph of the slope function for this piece, for this particular piece? Okay, we know that in this piece, in this interval, your slope is positive. At x is equal to 2, your slope is 0. That means your function, slope function, has to be like this. Would you agree with me? It has to be like this, because in this entire interval, your slope function has to be positive. That's why it is lying above the x-axis. But at x is equal to 2, I know that the slope is 0, because the tangent at x is equal to 2 is horizontal. And on the other hand, notice that to the right of 2, everywhere your slope is negative. For example, if you take a point somewhere here, and if you draw a tangent line here, the slope of this tangent is negative, because it slants, that tangent line slants downwards from left to right. Okay, so the tangent slope of this tangent is negative. As you can see, everywhere to the right of 2, the slope is negative. So your graph should look like this. Should go like this. Okay, this is the value 2. You might ask me why I chose this particular shape, like a curved shape. How do you know that you have a curved shape? No, I don't know. Okay, you can only give a rough sketch here. Someone could draw this graph like this. Oh, pardon me. Someone could draw this graph even like this, like a straight line which passes through this point 2. It is still correct. Okay, this is a rough sketch. By the way, this point is 2. Okay. All right, that's the slope function for this given function. Now let's look at one more example of this nature. Let's try to draw the slope function for this given function, y is equal to h of x. This is the graph of y is equal to h of x. We need to draw the slope function. Slope function is denoted by h prime of x. Okay, slope is denoted by this prime symbol, h prime of x. So how do you draw the slope function for this function? Well, first of all, let's try to identify a few things, okay? In this interval, what is the sign of your slope? In this entire interval, your slope is positive. As you can see, if you take any point in this interval and draw a tangent to your f of x at that point, the slope of that tangent is positive. Okay, so that means for all the x values in this interval, the slope of your function is positive, but at x is equal to -1, the slope is 0 because the tangent, if you draw a tangent at x is equal to 1, that tangent is horizontal. That means the slope is 0. Okay, so that means in this interval, in this entire interval, slope has to be positive, but at x is equal to -1, slope is 0. So you should have a shape like this. Tell me whether you agree with me. You should have a shape like this. What does this tell you? In this interval, your slope is positive. That's why this piece is above the x-axis, which says it is positive. And at x is equal to -1, your slope is 0. That's why it is coming and come and crosses the x-axis at x is equal to -1. And then let's think about this interval. If you look at this interval, on this interval, your slope is negative because this function is decreasing, right? On that entire interval, your function is decreasing. Decreasing means you have a negative slope. No matter what value you pick in this interval, if you, for example, pick your x value here to be this particular value, and if you draw a tangent here, the slope of that tangent is clearly negative. Likewise, if you choose any point in this interval, the tangent at that point is negative because your function is, of course, decreasing. If your function is decreasing, the slope is negative, okay? So that means for all the x values in this interval, your slope has to be negative, okay? So, but notice that at x is equal to 2, your slope has to be 0, okay? Between -1 and 2, your slope has to be negative, but at x is equal to 2, your slope has to be 0. So you should have a shape like this. Notice that between -1 and 2, your slope is negative. That's why it lies below the x-axis. But at x is equal to 2, your slope has to be 0 because this tangent is horizontal. Okay, that's why it comes and touches the x-axis here. Okay, actually it is going to cross the x-axis. You will see that. And then let's think about the other piece, last piece of the function. Okay, here in this piece, if you look at this piece, your graph is increasing, right? When you go from left to right, your function is increasing. Okay, so and if you look at this interval, if you pick any x value in this interval, as you can see from this graph, the slope is positive. For example, pick a x value here, and then if you draw a tangent here, the slope of that tangent is positive, right? Likewise, you can see that if you pick any x value to the right of 2 and draw a tangent to your function g of x, the slope of that tangent is positive. So that means the slope of your function for this piece is positive. So you should have a shape like this. course, you should have arrows like this. Okay, for this entire interval, on this entire interval 2 to infinity, your slope has to be positive. That's why this piece lies above the x-axis. The slope should be positive. Okay, so that's the slope function. Again, you might ask me the question, why did you made it curve like this? Okay, can you draw a straight line like this? Can you draw a graph like this instead? Yes, you can draw a graph like this. This is just a rough sketch. Okay, remember this is a rough sketch. Should put an arrow here, a small arrow. All right, next I want to introduce the idea of a secant line. The slope of the secant line of a function from A to B is given by f of b minus f of a divided by b minus a. What does that mean? Let's say you are given a graph of the function f of x to be like this. And then here is your a and here is your b. Then clearly this is your f of a and this is your f of b. Okay. Now what I'm going to do is I'm going to join these 2 points. This point and this point. If I join those 2 points, we get a line. Okay. This line is called the secant line of f of x from A to B. This is what you call the secant line of our function f of x from A to B. What you do is you mark these points, you find the y value corresponding to A, which is f of A, you mark this point, and you mark this point on the graph. This is the point B comma f of B. Notice that this is the point B comma f of B. And this is the point A comma f of A. You join these 2 points to get the secant line. That's what we call the secant line. And then the slope of this secant line is going to be this quantity. Okay, the slope is found using this formula that you learned in your pre-calculus class. Slope is y2 minus y1 divided by x2 minus x1. Okay, of course, if you view this as your x1 y1 and this as your x2 y2, and if you apply this formula, you are going to get this as the slope of this secant line. Okay, so that's the idea of secant line. Now we can use the slope of secant line to approximate the slope of a function at x is equal to a. That's what we are going to do next. Okay, approximation for the slope of f of x at a point x is equal to a. Let's say your point x is equal to a is here. Then I want to approximate the slope of my function f of x at x is equal to a. First of all, what do you mean by the slope of the function at x is equal to a? That is the slope of the tangent to my function at x is equal to a, right? That is the slope of this line, this tangent line at x is equal to a. So I want to find an approximation for the slope of this tangent line. How do you get an approximation for the slope of that tangent line? Well, the idea is I'm going to find a nearby point. I'm going to take h to be a small positive quantity. Okay, h is a small positive quantity. Then my a plus h would be a point to the right of a, somewhere here, right? If h is a small positive quantity, then I can find the corresponding y value. The corresponding y value would be f of a plus h. And of course, the corresponding y value here would be f of a, because your x value is a. Now what I'm going to do is I'm going to join these 2 points to get my secant line. okay? This point and this point. If I join those 2 points, this is the secant line I come up with. Okay, in red is the secant line from A to A plus H. Okay, now I'm claiming that I can approximate the slope of this green line by the slope of this secant line. Would you agree with me? This would be a good time to pause your video and check if this is true. Well, what happens here is that if you choose your H to be small, then of course we can approximate the slope of this green line by the slope of this secant line. Okay, for example, suppose you choose your H to be smaller, more smaller. That way your A plus H, if you choose your H to be smaller, then your A plus H would be somewhere here, right? You come your X value comes even closer to A. In that case, your function value is here. Now, if you draw your secant line, remember now this is your A plus H, okay? Now, if you draw your secant line, it would be a line like this. As you can see, slope of this secant line is more closer to the slope of the green line than the slope of this original secant line. Likewise, if you choose your H very small, then your A plus H would be very close to A. In that case, if you try to draw your secant line, that secant line and the green line, they almost look the same. What does that mean? That means their slopes have to be approximately equal. Okay, so the idea is that you make your H smaller. Okay, so that means the slope of f of x at x is equal to a can be approximated by the slope of this secant line, provided your H is small. Okay, so here is the idea. F prime of A is approximately equal. This is the symbol for approximately equal. Okay, is equal to f of A plus H minus f of A divided by A plus H minus A. Notice that you can view this as your point A, this as your point B, okay, to get the slope of the secant line using this formula. So this is what you get. Of course, you can cancel this A and minus A. Then you get, this is f prime of A is approximately equal to f of A plus H minus f of A divided by H. Okay, that's the approximation formula. Remember, this is true for H small. We need to make a note of it, okay? For H small, H close to 0, okay? H is approximately equal to 0. When H is approximately equal to 0, this can be approximated by this expression. That's the idea. All right, here is a remark of what we said. Slope of f of x at x is equal to a is approximately equal to f of a plus a minus a plus h minus f of a divided by h for h small, or in other words, f prime of a is approximately equal to f of a plus h minus f of a divided by h. All right, now let's look at an example. Look at this particular example. Y is equal to s of t is the distance of an object at time t. Find an approximation for the speed at t is equal to 1, given that s of t is given by this particular function. This is the distance is in feet. Okay. So first of all, I want to recall some concepts from physics. Okay. Might not taken a physics course, but don't worry, you need to know these definitions. Okay. Speed at time t is equal to 1, remember the speed at time t is equal to 1 is the instantaneous rate of change of distance at t is equal to 1. Okay, that's how we define the speed at t is equal to 1. Okay, that is the instantaneous rate of change of distance at t is equal to 1. What does that mean? That means s prime of 1, or the slope of the distance function at t is equal to 1, which is denoted by s prime of 1. Okay, slope of the distance function at t is equal to 1 is the instantaneous rate of change of distance at t is equal to 1, which is the speed at t is equal to 1. Okay, so some concepts coming from physics. So that means at the end of the day, we want to find s prime of t. We want to find an approximation for s prime of 1. Okay, so how do we find an approximation for s prime of 1? Well, we can use the formula that we just discussed. Okay, remember, this is an approximation. This is an approximation for f prime of a. Okay, so we can do a similar thing here. By the way, this is the graph of s of t. Okay, if you graph your function s of t, you will get a shape like this. Of course, it's a parabola, but I have not drawn the left-hand side because t is always positive. Okay, and also the distance is positive. So here is the piece of function that we are interested in, and we need to find the slope of this s of t. That means the slope of the tangent at this point at x is equal to 1. Okay, that's what we are interested in, which is denoted by s prime of 1. Okay, slope of s of t at t is equal to 1. All right, to find an approximation, I can use this approximation formula. S prime of 1 is approximately equal to s of 1 plus h minus s of 1 divided by h. I have to choose this h to be a small number to make sure that this is a good approximation for the speed at t is equal to 1. Okay, s prime of 1 is the speed at t is equal to 1. Well, we can try several values. Okay, to get, I'll try this one, s prime of 1. I'll take my h to be 0.25. Then you get s of 1 plus 0.25 minus s of 1 divided by 0.25. Of course, you can calculate this one. This is 1.25. Now you can calculate s of 1.25 by plugging 1.25 in your function. Okay. Similarly, you can find s of 1 by plugging 1 in your function s of t. If you calculate this, you will get this value, minus 36. And we can do another approximation. I'll try to find a better approximation, choosing h to be 0.1 this time. Okay. Then you will get s prime of 1 is equal to s of 1 plus 0.1 minus s of 1 divided by 0.1. This will give you minus 33.6. Okay, to find this one, of course, this is 1.1. You plug in 1.1 in your function s to find s of 1.1. Similarly, to find s of 1, you plug in 1 in the function s of t. Okay, so that will give you this quantity to be minus 33.6. As you can see from this graph, this approximation would be a better approximation because 1.1 would be somewhere here, 1.25 would be somewhere here. Okay, 1.1 is here, 1.25 is somewhere here. As you can see, this secant line would better approximate the slope at this point than this secant line. Okay, this is the point 1.25. So this would be a better approximation for s prime of t. Okay, s prime of 1, pardon me. S prime of 1 is nothing but the speed at t is equal to 1, or the instantaneous rate of change of distance at t is equal to 1. Okay, so of course you can keep obtaining better and better approximation by choosing this h to be even small. And here is a definition for the instantaneous speed at time t is equal to a in general. In the previous example, we talked about the instantaneous speed at t is equal to 1. But here is how you define the instantaneous speed at t is equal to a in general. Okay, so what you do is you take the limit as h approaches to 0, s of a plus h minus s of a divided by h. Okay, to approximate the instantaneous speed at t is equal to a, you just consider this quantity. You don't take the limit and you take your h to be a very small number, just like what we did in the previous example. You chose your h to be a small number, okay, to approximate. But if you want to find the exact value of the instantaneous speed at t is equal to a, what you do is you find the limit of this quantity as h approaches to 0. That will give you the instantaneous rate of change of s, or rate of change of distance at t is equal to a. Okay, so that's the last definition I wanted to talk about. All right, with that, we conclude section 2.1. And in section 2.2, we will be giving a formal definition for the derivative. Okay, I will stop there.